In this video, we're just going to look at finding the analytical solution for exercise 8F in section 1.2. The main thing that's complicated about this is the y integration. I've already separated the variables here in the first step. For the y integration, we're going to use the technique of partial fractions. This is a first step here in that method. Hopefully, the method of partial fractions, not to be confused with integration by parts, but partial fractions is hopefully something you learned in Calc 2 and may or may not remember. It is a skill that we will be using a lot later on in the course when we get to Laplace transforms. So it's well worth our while to review how to do it here. So we assume that there is a partial fraction expansion of that expression, the integrand, a partial fraction expansion of that form. There are some more complicated rules about partial fractions which we'll look at later on, but in this example we only have two simple linear factors, so we just have one term for each of the two linear factors. After we clear the denominators, we have, whoops, that's a pretty crazy check mark. Well, somewhere near the top of that check mark, the -1 equation is just from clearing the denominators on both sides of the previous equation. Then we take that equation and we plug in y values that make it convenient to solve for the two unknown parameters a and b. If we plug in y equals 4 into this equation, we get the equation -1 is equal to 4b, and solving then we find the value of b is -1/4. Similarly, by plugging in the value y equals 0 into that equation, we get the equation -1 is equal to 4a, which solving gives us the value of a is -1/4. Then we take those two values which we just found and plug them back into the equation that we've been working with here, or really more accurately, now that we've found a and b, we plug them back in up here in our original expression for the integrand. So that's what's happening right here. So now we take that new expression for the integrand. If you feel like it, you can check, use, and find a common denominator and verify that the right-hand side of that expression is indeed equal to what we started with. You can go ahead and do that if you feel like it, depending on how much review of this technique you want. Assuming that's correct, then doing the y integration here, there's another funny check mark, sorry about that. I'm still learning how to use all this technology. So doing that y integration, now it's straightforward to do the y integration. The first term was just an immediate plug into our good old natural log, and the second term we here on the right hand side is just an easy integration by substitution. Don't forget your minus sign. So that's going to give you this expression here for the y integration. And we set that equal to t integration, which was done a long time ago. We only need one constant of integration here. Usually it's convenient in a situation like this to isolate your natural log or exponential, in this case our natural log. So that's what I've done here, multiplied both sides by -4. Then I use the log property to combine those into one term, getting ready to exponentiate both sides, which is what's happening here on the top of page 6. Exponentiating both sides, we get absolute value of y over 4 minus y is c e to the minus 4t. And just as we've been doing for a while now on all these separable DEs, we redefine our constant if we feel like it as we go along to simplify the form of the solution. In the next step, we drop the absolute value At worst, we're off by a plus or minus 1. If necessary, we redefine our constant. Now we're trying to solve for y if we can. We started with a separable differential equation, so it's not always easy or convenient to solve the solution for y. Sometimes we have to be happy with just an implicit solution, as we've seen. But here we do want to go ahead and solve for y. So that's what's happening in this next step, just a little bit of rearranging. Then I multiplied out on the right hand side in order to have the terms that only involve y. And in the next step, I collected the terms that involve y on the left-hand side and factored out y. And that gives me this equation for y, which I then solve for y in the next step. We can still simplify that a little bit more if we divide by c and multiply by e to the 4t. That will get rid of the c upstairs. That will get rid of the exponential upstairs. That will introduce e to the 4t in one term in the denominator, this term here, and it will get rid of everything in the other term. So again, redefining the constant if we feel like it, we end up with our analytical solution here, where, as I point out, we've redefined the constant c again, and that's usually how you would write the analytical solution for a problem like this. It's a little bit of work, a little bit of integration, and a little bit of rearranging gives us the analytical solution to the differential equation that we started with. And now it's easy to see what happens with the long-term time behavior, depending on your initial condition, of course. But in a typical problem where you're between your two equilibrium values, y equals 0 and y equals 4, we said that y equals 0 was a stable equilibrium. We said that geometrically earlier, and we see our analytical solution agrees with that.